impulse reaction turbine. The problem is given like this. At a particular stage, of a reaction turbine, the mean blade speed is 60 meters per second and the steam pressure is 3.5 bar with a temperature of 175 degrees centigrade. The identical fixed and moving blades have inlet angles of 30 degrees and outlet angles of 20 degrees. Determine number 1, the blade height if it is 1/10 of the blade ring diameter for a flow rate of 13.5 kg per second. Number 2, the power developed by a pair of blades. And number 3, the specific enthalpy drop if the stage efficiency is 85%. The solution to this problem is given in this manner. First of all, from steam tables, we take a specific volume of steam at given conditions of 3.5 bar and 175 degrees centigrade is taken as from the tables 0.572 meter cube per kg. Now let us draw the velocity triangles of Parsons turbine, Parsons reaction turbine, otherwise known as. How do we know that the given turbine is Parsons reaction turbine? In the problem, it is given that the identical fixed and moving blades only for the Parsons reaction turbine, that is 50% degree of reaction turbine, we have identical fixed and moving blades. We have seen it earlier also. Alpha is equal to phi and theta is equal to beta in the case of the 50% degree of reaction turbine, where the enthalpy of steam equally drops between fixed blades and moving blades. Now drawing the velocity triangles on the common base of a blade velocity. This is V1, VR1, VR2, this is V2. This is U, which is given. U is given as, in the problem, U is given as 60 meters per second. Alpha is given as the inlet angles of the fixed and moving blades are given as alpha is equal to phi. There phi is the moving blade outlet angle, which is given as 20 degrees, whereas theta is equal to beta is equal to 30 degrees. Now dropping the perpendiculars, we get this is alpha, this is phi, this is theta, this is beta, this is VW1, that is variable component of absolute velocity, this is VW2, this is VF1, this is VF2. Okay, this is the velocity triangles for the 50% degree of reaction turbine. Now let us try to solve the problem. Analytical method. From the triangles we can find that V1 cos alpha minus U is equal to X. Let us call this as X, which is equal to VF1 divided by sin theta, implies V1 cos alpha minus U is equal to V1 sin alpha divided by sin theta. Put alpha is equal to 20 degrees, theta is equal to 30 degrees, and U is equal to 60 meters per second. So from this equation V1 is obtained. Once V1 is obtained, VW1 is equal to V1 cos alpha. From the symmetry of velocity triangles, about the vertical axis, bisecting U, we can say that X is equal to VW2. How so? VW2 is obtained as V1 cos alpha minus U. It is nothing but VW2. So many meters per second. Having obtained VW1 and VW2, we can calculate diagram power or work done per second by steam on the moving blades as mass flow rate of the steam into VW1 plus VW2 into U. So many Newton meter per second. Mass flow rate of the steam is given in the problem as 13.5 kg per second. It is given in the problem. So diagram power could be calculated from the above formula, which is obtained as 218 into 10 cube watts. This is nothing but watts. Power is directly given in watts with this formula. M dot of the steam into VW1 plus VW2 into U. That is the power obtained in watts. So we got the diagram efficiency. Now, when you come to the blade height, so what is blade height? That is a problem now. The mass flow rate of the steam can be obtained as volume flow rate of steam divided by specific volume of steam. What is the volume flow rate of the steam? Area of flow. Area of flow into velocity of flow, Vf1 or Vf2, divided by specific volume. What is area of flow? Pi d h, where d is the diameter of the rotor and h is the height of the blade. The flow is parallel to the axis of the rotor. Even Parsons turbine is axial flow steam turbine. That is the reason why at inlet of the moving blade and at exit of the moving blade we are writing same blade velocity u, because the Parsons turbine is axial flow reaction turbine. So for axial flow reaction turbine, the area of flow is pi dh, where d is the diameter of the rotor and h is the height of the blade, into velocity of flow Vf1 divided by specific volume. That is mass flow rate of the steam, which is given as 13.5 kg per second. Diameter of the rotor is also given as it is 10 times h. It is given in the problem. Therefore, it could be substituted d in terms of 10 times h. That is mass flow rate of the steam is equal to pi into 10h into h into Vf1 divided by specific volume is equal to 13.5 kg per second. But how to get the Vf1? That is the problem. Now, having known V1, Vf1 can be obtained as flow component of absolute velocity is equal to V1 sin alpha. V1 is calculated earlier and alpha is given as 20 degrees. We can easily obtain Vf1. In fact, in this problem, Vf1 is obtained as 60 meters per second So height of the blade could be calculated as 0.064 meters, which is equal to 64 millimeters. Now coming to the stage efficiency, till now we didn't define the stage efficiency. It is defined as work done per second or per kg by the steam divided by isoentropic enthalpy drop of the steam. Per stage, that is work done per kg divided by delta H per stage. Hence stage efficiency can be written as 1 into VW1 plus VW2 into U. This is the work done per kg of the steam divided by delta H iso per stage. It is given here as 0.85 in this problem. Implies isoentropic enthalpy drop per stage is equal to U into VW1 plus VW2 divided by efficiency of the stage, which is obtained in this problem as 19.1 kilojoule per kg. This is the answer for isoentropic enthalpy drop per stage. Now coming to another problem on the steam turbines, which is given as in a 50% reaction turbine, stage running at 50 revolutions per second, the exit angles are 30 degrees and inlet angles are 50 degrees. The mean diameter is 1 meter. The steam flow rate is 10,000 kg per minute, and the stage efficiency is 85%. Determine number 1, the power output of stage. Number 2, the specific enthalpy drop in the stage. And number 3, the percentage increase in the relative velocity of steam when it flows over the moving blades. The solution to this problem could be given like this. First of all, let us calculate mean blade speed, that is u, or tangential speed of the rotor, which is given as pi dn by 60 if n is given in rpm, but in this case n is given as revolutions per second. So there is no need to write 60 in the denominator. So it results in pi into diameter is 1, where revolutions per second is given as 50. So the resultant answer for u is 157 meters per second. Now let us draw the velocity triangles for the 50% degree of reaction turbine, which is also called as Parsons reaction turbine, on the common blade speed base u, like this. This is inlet velocity triangle. This is exit velocity triangle. This is V1, VR1, VR2, V2. Dropping the perpendiculars, we get the velocity components for the absolute velocity. Up to here it is u. This is VW1. This is VF1. This is alpha, theta, phi. This is beta. This is VW2. This is VF2. For 50% degree of reaction, alpha is equal to phi, theta is equal to beta. Alpha is equal to phi here given as 30 degrees. Theta is equal to beta is given as 50 degrees. Please note that fixed blades and moving blades do have the identical shape. So inlet angle of the fixed blade is equal to inlet angle of the moving blade. It should be noted here that the inlet angle of the fixed blade is same as the inlet angle of the moving blade, and also outlet angle of the moving blade is equal to the outlet angle of the fixed blades. That is the reason why both fixed blades and moving blades do have identical shape. Now let us calculate in the same fashion as the previous problem, that is V1. So let us call this as X. V1 cos alpha minus u is equal to X, which is equal to Vf1 divided by sin theta, where Vf1 can be written as V1 sin alpha divided by sin theta. In this equation, everything else is known except V1, because alpha is given as 30 degrees, u is we have calculated as 157 meters per second, theta is given as 50 degrees, and hence V1 could be obtained. So V1 is obtained. Once V1 is obtained, VW1 can be written as V1 cos alpha, and VW2 is equal to X is equal to V1 cos alpha minus u, that is from the symmetry of the figure about the vertical axis. Having obtained VW1 and VW2, we can calculate the diagram power output. Is equal to mass flow rate of the steam into VW1 plus VW2 into U, which is obtained here as 11.6 into 10 power 6 watts, which is equal to 11.6 megawatts. Now this is the answer for diagram power. Now coming to the stage efficiency, which is defined as U into VW1 plus VW2 divided by delta H isoentropic. Numerator is work done per kg divided by isoentropic enthalpy drop in a stage. So therefore delta H isoentropic is equal to work done per kg divided by stage efficiency, which is calculated as 157, that is U, into 444 divided by 0.85. It is obtained as 82,000 joule per kg. This is isoentropic enthalpy drop per stage. Coming to the third, that is percentage increase in relative velocity. Now let us have to calculate VR1 and VR2. Sin theta is equal to VF1 divided by VR1. What is VF1? V1 sin alpha divided by VR1. Therefore relative velocity at inlet is equal to V1 sin alpha divided by sin theta. Because V1 is already calculated above, we can calculate VR1 as 224 meters per second. And how to get VR2? VR2 is equal to V1, which is obtained as 341 meters per second. Therefore, percentage increase in the relative velocity is equal to VR2 minus VR1 divided by VR1 into 100. That is 341 minus 224 divided by 224 into 100. That is 52.2%. This is the problem. Now I shall solve an objective question given in GATE 2005. The question is given like this. In the velocity diagram shown below, U is equal to blade velocity, C is equal to absolute fluid velocity, and W is equal to relative velocity of the fluid, and the subscripts one and two refer to inlet and outlet. The figure is given like this. he has given U1 is equal to U2. This is given as W2, that is the relative velocity. This is given as C2. This is given as W1. This is given as C1. Now from the figure we have to decide the velocity triangles given are for A, an impulse turbine, B, reaction turbine, C, centrifugal compressor, D, axial flow compressor. That is the 4 options given there. What is the answer? The velocity triangles given in the figure are corresponding to what type of machine? The solution to this gate problem is given like this. In an impulse turbine, that is degree of reaction is equal to 0, whose name is de-level steam turbine, relative velocity at exit, which here in this case as W2, in this particular problem it is denoted as W2, is greater, is always lesser than W1 or VR1, relative velocity at inlet. Maybe it is equal if it is frictionless. If the blade is frictionless, moving blade is frictionless, then VR2 will be equal to VR1. If there is friction, VR2 is less than VR1. That is W2 should be lesser than W1. But in this case, in the given figure, W2 is greater than W1. Therefore, the answer cannot be impulse turbine. If you look at the reaction turbine, in reaction turbine, VR2, that is W2 in this case, what is given denoted, is always greater than VR1 or W1. So, in the given figure, W2 is greater than W1. Therefore, answer should be reaction turbine. Therefore, answer is reaction turbine. But if you look at the centrifugal compressor, for centrifugal compressor, and axial flow compressor, relative velocity at exit of moving blade is lesser than relative velocity at inlet. So C and D cannot be the answer. So the answer final is reaction turbine. The velocity triangles are meant for reaction turbine. In fact, the given triangles are for Parsons impulse reaction steam turbine, whose degree of reaction is 50%. Now, I shall solve a problem on steam nozzle. Steam expands from 3 bar to 1 bar in a nozzle. The initial velocity is 90 meters per second and the initial temperature is 150 degrees centigrade. The nozzle efficiency is 0.95. Determine the exit velocity. Now the solution to this problem could be given. Let me represent the expansion of the steam in the nozzle on Mollier diagram, that is enthalpy versus entropy, kilojoule per kg enthalpy, entropy is kilojoule per kg Kelvin. This is the dry saturated vapor line. This is 3 bar pressure line. The initial temperature is 150 degrees centigrade. This is the state of the steam at the inlet of the nozzle, which is expanding isoentropically, not actually isoentropically, because nozzle efficiency is given. The 1 to 2 dash is isoentropically, 1 to 2 is actual expansion. This is 1 to 2 dash is isoentropic expansion. 1 to 2 is actual expansion with friction. Therefore, nozzle efficiency is given as H1 minus H2 divided by H1 minus H2 dash, which is given as 0.95, 5% loss due to friction. This H1 is nothing but H soup, enthalpy of the superheated steam at 3 bar, 150 degrees centigrade. From steam tables, it is given as 2762 kilojoule per kg. And similarly, S1, that is entropy of the superheated steam at 3 bar, 150 degrees centigrade, it is given as 7.078 kilojoule per kg Kelvin. These two are picked up from the steam tables. Now let us discuss about supersaturated flow or metastable flow through nozzles, steam nozzles. Now if we draw the expansion of the steam through the Mollier diagram, through the nozzle, if this is inlet pressure of the steam supplied to the nozzle, when the steam is expanding isentrically, say from A to B and then further down, the condensation of the steam should begin at B. But because the steam particles are moving with high velocities, they don't get enough time to come together and thereby form a condensed liquid. Therefore, condensation is delayed. It would not occur at B. It would occur at a point below B, say at a point B1. Let us denote this point on a B1 on a line called Wilson line. Wilson line is the locus of all the points where the condensation is suddenly appearing. Between states B and B1, the steam is not under thermal equilibrium, and such flow of the steam where the condensation is delayed due to the inertia of the steam molecules is known as metastable flow or supersaturated flow. Now let me write this point very categorically, that regarding the supersaturated flow. During the expansion, the change of phase must start to occur at pressure P2, that is where the expansion line meets the saturation line, that is at point B. While the steam is expanding, as is shown in the isoentropic line, the condensation should begin at point B, but this pressure is P2, I can say, but the condensation is delayed. It would occur below B, that is at point B1. But in nozzles, this phenomenon of condensation does not occur at B, as the time available, that is for condensation, is very short due to very high velocity of steam. Passing through the nozzle. Therefore, the equilibrium between the liquid and vapor phase is delayed, and the vapor continues to expand in dry state even beyond point B. Even beyond point B. It is supposed to condense at B, but it would not condensing. This is represented by B1. The steam during the expansion BB1 remains dry and condensation is suppressed. The vapor between B and B1 is said to be supersaturated, and such flow is called supersaturated flow. Point B1 where condensation suddenly happens lies on Wilson line. This line is called Wilson's line. Now I shall define reheat factor. Consider a multi-stage expansion in the turbine on Mollier diagram. This is the dry saturated vapor line. These are the different isobaric lines indicating the expansion of the steam through multi-stages. The figure shows the expansion of steam through a number of turbine stages. A1 B1 represents the isoentropic expansion in the first stage. One stage of turbine means a row of fixed blades followed by a row of moving blades. The actual state of steam with frictional reheating is shown by line A1, A2. Therefore, the actual heat drop is equal to A1 C1, where it can be taken as C1. Similarly, the isoentropic and actual heat drops in the succeeding stages are shown in figure by A2 B2, A3 B3 and etc. and A2 C2. What is A2 C2? This is the actual enthalpy drop, whereas A2 B2 is the isoentropic enthalpy drop in the second stage. This is first stage. A2 C2 comma A3 C3. What is A3 C3? This is C3. That is, if C3 point is obtained by drawing horizontal line leftwards through A4, like that, and so on. The drop A1D represents isoentropic heat drop or Rankine heat drop between supply state and condenser state of steam. The reheat factor is defined as the ratio of the cumulative enthalpy drop to the Rankine enthalpy drop and is given by, from the figure, reheat factor is equal to A1 B1 plus A2 B2 plus A3 B3 plus etc. divided by A1D. reheat factor always is greater than 1 and lies between usual value of the reheat factor is 1.0 to 1.06. More the reheat factor, I can say lesser the stage efficiency across the stage. More the reheat factor, lesser the stage efficiency between the stages. Now match the following lists. List 1. List 1 gives different types of turbine stages and list 2 gives names of turbines. List 1 A 50% reaction stage, B single stage impulse turbine, C two-stage velocity compounded turbine, D 100% reaction stage, E two-stage pressure compounded turbine. List 2 has got number 1 Ratu, number 2 Parsons, number 3 D-level, number 4 Curtis, number 5 Heroes. The answers are given like this. The solution to this is 50% degree of reaction is exactly matches with Parson. Single stage impulse turbine, we know that it is pure impulse turbine, that is D-level, that is 3. C two-stage compounded velocity compounded turbine is a Curtis turbine, that is 4. D 100% reaction stage is Heroes. We already know it. This is a Heroes turbine, is a pure reaction turbine. This is pure reaction turbine. E two-stage pressure compounded turbine shall match with 1, that is Ratu turbine. Compounding of steam turbines, here we should take a note that compounding of steam turbines is done to reduce the high rotational speeds of rotor so that it can be directly coupled with the generator, that is by allowing the steam to expand in stages. There are two types of compoundings, namely pressure compounding and velocity compounding.